Up till now we have seen that under pure bending what will be the distribution of stress across cross section, where the neutral axis will lie, and what is the effect of changing the moment of inertia of a cross section or the farthest distance of a fiber from the neutral axis. All these concepts we have derived and seen in the form of equations. Now, one thing still we haven't derived is the radius of curvature through which it will be bent. For example, when we saw that once we apply the moment, an arc of a circle is resulted in, and whose radius was rho, if we remember. Yeah, so let me draw this. So you had like this. Okay, and so we had applied moment m in both the ends. So these convention of moment, this sign of moment was considered positive conventionally, and then these things met at a point which was the center of curvature. In fact, all the sections of the beam were pointing towards that, right? So if you join anything, so they will go and meet there. Anyways, so we are now trying to find out this. Suppose here is the neutral axis, and we are trying to find out what is this rho. Now, we had derived one equation saying that the strain, the longitudinal, the axial strain was negative of y over rho, right? Yeah. So y over rho was the longitudinal strain, and from there we said that epsilon max was negative of c over rho. Okay, and in fact the negative sign, to see the absolute value of EM, we just said that it's at c over rho. From where we can write that 1 over rho, which is the curvature, is nothing but your EM over c. If we just neglect the sign, okay, because EM is the absolute value we are taking. Yeah, so in fact, okay, we can do like this. That makes everything consistent, whatever we have used. But then this one we can write now as what? Sigma m over EC, right? So that's what we can write if we are under the linearity condition, and then oh sorry, oh here then, okay, fine. So what we had got here, sigma m is mc over I. So we will replace this thing or substitute this here. So in place of sigma m, we will replace mc over I. So mc over I times 1 over EC. So that gives you m over EI. So I'll just write the summary here. 1 over rho is equal to m over EI. So this is one of the very famous equations related to pure bending of Euler beams, okay, where the deformation due to shear is not considered, okay, though we can calculate the shear stresses, but the deformation due to them is not considered. Okay. Now what this equation tells you is that you can calculate the radius of curvature through which the beam bends under a particular moment that you have applied, and here you see this, if you call this as curvature, that means how curved the thing has become. The more the moment, the more the curvature, obvious. And then these two things you just observe, one of them is a material property and the other one is a geometric property. Okay, but both of them are contributing towards the radius of curvature for a given applied moment. If you increase a material whose E is higher, then your curvature will be reduced, that means the rho will increase, the radius will be increased, that means it will be more flat, okay, it will not be curvy for the same moment. Similarly, if all other things are constant, say the same moment you are applying, the same material you are using, but if you want the bend to be less, what you need to do is you have to somehow increase the moment of inertia, and that precisely is done you must have seen cross sections like this, right? So, which are called I sections. Now, if these are the cross section, so why it is preferred over a rectangular is by distributing the mass in this form, what we have done is we have increased the moment of inertia for the same amount of mass. By that we have reduced the curvature, or we have increased the radius, that means the bending effect has been reduced. Okay, so that is the reason why that distribution is made in such a way that the mass is distributed as far as possible from the neutral axis, because here the neutral axis will be passing somewhere in the middle and you want to distribute the mass as far as possible. And there is one point which you can see. See, if you just see this equation, previously we had defined, right? Sigma m was nothing but mc over I. Now, one point you should observe that in this effort of increasing the moment of inertia, because that's always is your aim to reduce this maximum stress that get developed, and then for that reason you always try to increase the moment of inertia, so that the bending also will be reduced, the stress will be reduced, everything is good. But in doing so, you will invariably increase C, right? Because you will distribute the masses farther and farther. So, the fiber from the neutral axis also will go farther. But then, but the point is, this moment of inertia depends as y squared dA, or I was using capital A for area, right? So, like this, right? Square of the distance, but this is moving at a linear fashion. So, the effect of increasing the moment of inertia will be predominant, and you will reduce the maximum stress that's developed. Now, so that was about the moment of inertia and the C value. But here, as I was saying, one part is material, the other part is geometric, and this product, the product EI, in fact, is as a combination, as a combined thing, they are responsible for checking the amount of bend that you are having for a given m, and that thing has got a name. It's called flexural rigidity. Okay. Now, flex means you bend like that, you flex your muscles, so you bend your muscles. So, this from there the flexural word has come, and rigidity again it's like a modulus kind of term. So this tells you that I can write this as EI is equal to m over 1 over rho, okay, or you can write m over say kappa. This is the curvature. So that means the flexural rigidity can be defined as like again a modulus, like moment required for unit curvature production. Just few minutes back we had discussed about section modulus, moment required for production of unit maximum stress, maximum normal stress, and here we are talking about moment per unit curvature is the flexural rigidity. That is where you can change the rigidity of a structure against bending by either increasing its Young's modulus or by increasing the moment of inertia about the neutral axis which is responsible for resisting the bending. So that is the thing which is very important, and in a way the Euler's beam theories, deformation and stress, these are the things for pure bending case in a way are complete now, and we will stop for this segment. We will see in the next segment about a very important concept which is called the shear force and bending moment diagrams, which are always required to analyze beams under different loading conditions. So, we see you in the next segment.